In this video we will be talking about infinity. Okay. Now if you go on the Wikipedia page, for example, you'll see the following definition of infinity. So they say infinity and they use this symbol for it. Okay, is a concept describing something without any bound or larger than any natural number. Now this definition is short, but I'm not sure if it clarifies what infinity is. So first of all, we use this symbol for it, which kind of implies that there is one infinity. All right, so that's one thing to think of. Okay, but now let's look deep into what infinity is. Okay, so when it comes to, for example, infinite sets, all right, probably the first one that comes to mind is the set of natural numbers. Okay, the set of numbers 0, 1, 2, 3, 4, 5, and so on. Okay, so it's kind of clear that this is not a finite set, so it's an infinite set. All right. Now, maybe the second example of an infinite set that comes to mind is a set of integer numbers. Okay, so now we have numbers like -2, -1, 0, 1, 2, 3, and so on and so forth. All right. Now, if let's say a primary school teacher will ask kids, okay, given these two sets, which one is bigger? Okay, probably a lot of kids will look at the two sets and they'll figure out, well, 0 shows up in n and it shows up in z. The same is true for 1, the same is true for 2, for 3, and so on and so forth. So n, which is this set here, appears in here also, right? But z has these extra elements. So it appears that somehow z is larger than n. Okay, well, so what does large mean? Okay, actually in math, in order to deal with this idea of smaller or larger when it comes to set, the notion of bijective functions is very, very important. This notion actually is very important throughout math, but more so when we talk about sets, how big they are. Okay, so anyway, we'll probably come back to this idea of bijective functions in future videos. So let's go back to us looking at these two sets. Okay, so we said that it looks like n is contained in z, so z is somewhat larger than n. Okay, now let's take a different look at these two sets. Okay, let me copy n again. So n is 0, 1, 2, 3. Let's write a few more of these elements, 5, 6, and so on. All right, and let's rewrite z in a slightly different way, because as you can see, z sort of doesn't have a beginning and it doesn't have an end. So okay, it's sort of a legitimate way of writing it like so. But how about we write it like so? Let's start off with 0. Okay, and then let's write the neighbors of it, which are 1 and -1. Okay, and then let's go to 2 and -2. All right, 3 and -3. So now we kind of see the pattern, right? Okay, so we continue like so. All right, so this set up here is our n, and this is another way of writing our z. Okay, now let me ask the question again. Which one is larger, n or z? Well, okay, so if we think of us being able to pair up 0 with 0, 1 with 1, 2 with -1, 3 with 2, 4 with -2, 5 with 3, and so on. Okay, well, if we do so, actually we construct what's called a bijective function. Okay, but let's not go into the technicalities of that. But anyway, looking back at this pairing here, it doesn't look like Z is bigger than N. Actually, it looks like Z has exactly the same number of elements as N. All right, so one look at the two sets shows that Z has more elements than N. Another look at the two sets with these pairings like so sort of make us think that Z is really not bigger than N. All right, so now I would think, well, infinity is a little bit of a tricky notion. All right, it could be the case that something looks bigger but is really not bigger than something else when the two objects, in this case, the two sets, are infinite. All right, good. So let's see, how about we look at what's the next set you can think of when it comes to numbers and infinite sets. Well, after learning about natural numbers and integer numbers, probably the next set will be the set of rational numbers. The set of rational numbers can be written like so. Okay, we can describe it as the set of fractions m over n with the property that m is an integer number and n is an integer number that's not 0. All right. So this is a little bit more abstract than this two other sets, n and z. Okay, we actually have a full description of it in here versus enumeration of the elements of n and z. All right. Now, so if you want to view Q, okay, here's what we can do. Let's say we take the real number line. Okay, so this is the real line, and on it we pick at some point 0, right? At some point 1, 2, or if you want, we go to the left, -1, -2, and so on. Okay, we can go all the way to the right and to the left. Okay, so now we've got all the integer numbers. Okay, where are the rationals? Well, halfway in between 0 and 1, we have, for example, 1 over 2. Halfway in between 0 and 1 over 2, we have 1 over 4. Okay, and we can keep doing so. All right, so we can look at the number that's halfway in between 1 over 4 and 1 over 2, and we get another one, okay, which will be rational. And then, you don't even have to go halfway. You can, fact is that there is infinitely many numbers. Given any two real numbers, there is infinitely many numbers that are rational. Okay, so given two numbers like so, okay, you will find a rational number in between the two. Okay, now mathematicians refer to this property by saying Q is dense in R. All right, so okay, I kind of described what dense means, but fact is that this picture here tells you that rational numbers are all over the place. Okay, as opposed to, let's say, integers. Here's 0, here's 1, here's 2, here's -1, -2, right? So very nicely spaced throughout the real numbers. Okay, no integer is in between 0 and 1, no integer is in between 1 and 2. Okay, that's not the case with Q. Q is all over the place. All right, now again, looking at this picture here, okay, which one is bigger, Z or Q? Well, clearly Q contains Z, and it has all these extra elements, so it looks like Q is bigger than Z. All right, let's see if we take another look at the two sets, let's say Z and Q, just sort of in the sense in which we took another look at the sets N and Z. All right, and here's what we are going to do. So first of all, let's only look at the positive rational numbers and the natural numbers. Okay, so if we take the positive rationals and we write them. Okay, how are we going to write them? Well, clearly, because of the fact that they show up all over the place, we cannot just write them by, their natural order. Okay, but here's what we can do. So let's say, let's write on a row here the positive rational numbers with a denominator, with a numerator, let's say, of 1. Okay, so it's 1 over 1, okay, 1 over 2, 1 over 3, 1 over 4, and so on. Okay, so on this row here, I'm going to write all the rational numbers with a numerator of 1. Okay, underneath, I'm going to write all the rational numbers with a numerator of 2. 2 over 1, 2 over 2, 2 over 3, 2 over 4, and so on. All right. Underneath, I'm going to write all the rational numbers with a numerator of 3. 3 over 1, 3 over 2, 3 over 3, 3 over 4, and so on. Okay, and we can keep doing so. Okay, 4 over 1, 4 over 2, 4 over 3, 4 over 4, and so on. All right, so I believe if you take a good look at this little algorithm that we have here of writing the positive rationals, you'll see, okay, eventually we will write all of them. Okay, if we keep going, eventually every single one of them will be written down. Okay, but there's something else going on in here. See, for example, we have 1 over 1 in here, 2 over 2 in here, 3 over 3 in here, 4 over 4 in here. Okay, so clearly these numbers are equal to each other. Okay, so if we keep doing this process, if we continue this process of writing down our rational numbers, we will write them all. Okay, but some of them will repeat. Actually, all of them will repeat, because look, for example, 2 over 1 shows up in here, and it shows up as 4 over 2 in here, and it will show up as 6 over 3, and so on and so forth. All right, so we have a lot of repetitions in here. Okay, now here's what we can do. How about we say, okay, so the first number is 1 over 1. All right, so this is our first number. All right, now let's go on this row. So the next one is 1 over 2. This is our second number. All right, now let's go on the diagonal. The next number is 2 over 1. Okay, this is our third number. Okay, now the next number, as we go down like so, is going to be 3 over 1. So this is our fourth number. So 1, 2, 3, 4. All right, so, but now just like we went on a diagonal here, how about we go back up on this diagonal here? So the next number will be 2 over 2. Well, 2 over 2 is 1 over 1. So we encountered 2 over 2 actually. So let's skip it, just because we had it before. All right, so we're not going to count this number just because it showed up in our little parsing algorithm before 2 over 2. Okay, 1 over 3. 1 over 3 did not show up before. Okay, so we are going to associate the number 5 with it. Okay, now we continue on this row here. 1 over 4 did not show up before, so we are going to associate the number 6 with it. Okay, and now we go back on this diagonal. So 2 over 3, we check again, it didn't show up before, so we are going to associate a number with it. And then we keep doing like so. All right, so basically what we did is we found a way of parsing these numbers. So we went like so, going down, and we went on diagonal like so, and then on a row, then back on the diagonal. Okay, so we kind of go in this little pattern of ours to go through the entire set of numbers. Okay, so and we skip the ones that we had from before, like 2 over 2 here. We just skip, we do not count them. All right, so now we can see that we associated with every single rational number a different integer. Here we have 1, 2, 3, 4, 5, 6, 7, and so on and so forth. Right? So actually, while this is a little bit more complicated than this, you'll see that the idea is the same. We just wrote the rational numbers in a clever way. Here, we wrote the integers in a clever way. Okay? So that we can come up with a mapping between the set 1, 2, 3, 4, 5, 6, 7, and so on and so forth, and the positive rationals. So now, which one is bigger? Q or N? All right. So basically, this picture here kind of tells us that Q is bigger than Z, while this picture here shows us that the positive rationals are not at all bigger than the integers from 1 and up. All right, so again, another idea showing that infinity is a little bit tricky to deal with. Okay, sets that appear big are not necessarily bigger than sets that initially appear smaller. All right, so infinity is a little bit tricky. All right, and now I'm gonna sort of finish up this video with a little question for you. All right, so let's see, if you look at this set here, 1, or this sequence, 1, 2, 3, 4, 5, and so on. All right, and so what would you write sort of at the end of it? What number or what symbol would you write on here? All right, now if you look at, okay, here, let's look at another one. Let's say 1 over 2, 2 over 3, 3 over 4, 4 over 5, and so on, right? So we get the pattern here. We write some fractions that whose numerator is 1 less than the denominator. What would you write here? So what do you write here? What do you write here? All right? So maybe think of the answer to this question and maybe try to get a different understanding at what infinity is.